This is a home studio rerun of a short talk given at the Accelerating Development of Energy Innovation Ecosystems Workshop at the University of Cambridge, June 18 to 19, 2023, hosted by Laura Anadon, Sergey Kolesnikov, Venki Narayanamurthy, and Evan Michelson. Good morning. Thank you, Laura, Gabe, Venki, and Evan for the invitation to participate in your workshop. As some of you know, I've been a researcher in the physical sciences and engineering for most of my career. In my mid-career, working on one piece of the energy innovation ecosystem, solid-state lighting, whose key enabler was the blue light-emitting diode depicted here on the left. That invention in 1993 had all sorts of repercussions. The 2014 Physics Nobel Prize to Akasaki, Amano, and Nakamura. When it's all said and done, a 3 to 4% decrease in world energy consumption, a huge burst in energy-related research as illustrated by the sudden increase in 1993 in density of papers on this citation dot chart. And by 2017, a packaged chip revenue of $15 billion per year, a non-negligible fraction, something like 5% of silicon, which is amazing considering the reach that silicon technology has into modern society. At the same time, as most of us here know, Venki has been hard at work this past decade articulating how science and technology don't advance in a vacuum. They advance interactively in cycles. One of those cycles between science and technology was the topic of his first book in 2016, while other cycles were the topic of his second book in 2021. So what I'd like to do today is describe how these cycles unfolded in solid-state lighting to illustrate the importance of an innovation ecosystem that supports all the cycles. Let's start with a super brief introduction to the technoscientific method, which is Venki and my name for the interacting mechanisms and therefore the cycles by which science and technology advance. There are two main ideas. The first idea is that there are two repositories of technoscientific knowledge, science and technology. The science repository, S in uppercase and in blue on the left, has two bins, facts and explanations of those facts. The technology repository, T in uppercase and in green on the right, also has two bins, human desired functions and forms that fulfill those functions. The second idea is that the evolution of those two repositories of knowledge is mediated by the technoscientific method, the interacting combination of the scientific method, what we call S dot, and the engineering method, what we call T dot. The engineering method on the right starts with 1, the finding of human desired functions. Then with functions in hand, the method proceeds to 2, the finding of forms that fulfill those functions. With forms in hand, the method proceeds to 3, exapting, the co-opting of existing forms to fulfill functions they were not originally intended to fulfill. The scientific method on the left starts with 4, the finding of facts. With facts in hand, the method proceeds to 5, the finding of explanations for those facts. And then with emerging explanations in hand, the method proceeds to 6, the generalizing of those explanations to predict possible new facts, triggering a hunt for those new facts. Before we move on, let me make one overarching point that we believe that this technoscientific method, as practiced by humans to advance science and technology, is complete. Every mechanism is necessary, and there are no additional mechanisms. That means if we want to build a healthy innovation ecosystem, we need to be sure all the mechanisms are healthy. Okay, let's now turn to a 10,000-foot historical view of solid-state lighting, viewed through the lens of how the various mechanisms of the technoscientific method were exercised and ultimately built on each other to advance solid-state lighting as a whole. I don't have time to go through the advances in detail, but let me at least describe the broad groups of advances. First, there were the human desired functions functions that provided the initial motivation: flat panel displays and optical storage. Second, there were the engineered forms that enabled those functions, including the pivotal invention in 1993 of the Candela-class blue LED. Third, there were the human-desired functions that these forms, particularly the phosphor-converted white LED, were exapted for, particularly solid-state lighting, which was not on the radar screen at first, but ultimately became the killer app for these forms. Fourth, these engineered forms not only fulfilled these new functions, they also they were directly useful to human society. They also went against conventional expert scientific wisdom. They represented facts that overturned existing, hence required new scientific explanations. So these engineered forms played a dual role, fulfilling engineering functions and providing new scientific facts with no explanation. Fifth, new scientific explanations did gradually appear. Sixth, these scientific explanations began as hypotheses requiring testing. So tons of experiments were done to eventually codify these hypotheses into a revised expert scientific wisdom. And finally, to come full circle, this new expert scientific wisdom was used to improve subsequent generations of engineered forms, including in 2011, the white LED that first made break even, that first had a lower life ownership cost than incandescent lamps, and therefore that initiated the mass conversion of general illumination to solid-state lighting. Let me close with 3 takeaways. First, exaptation was essential to ultimate success. SSL, solid-state lighting, was not the initial motivator, and indeed was so far-fetched a possibility in the 1980s that it couldn't have been the initial motivator. It was only after the phosphor-converted white LED was invented that SSL became a glimmer in some people's eyes, and even then, there was huge skepticism. Second, surprise and contrariness were essential. The 1988 breakthroughs required Akasaki, Amano, and Nakamura to go against the conventional expert scientific wisdom of the time. Third, engineering led science, not the other way around. Indeed, this makes vivid the important role that technology plays as the source of unexpected new scientific facts, in contrast to the common view that an interest in advancing technology implies a disinterest in advancing science. With that, thank you.